Hello everybody, this is the third and last video for chapter 6 of the statistical learning course. So chapter 6 was about introducing decision tree methods for prediction or classification. And we've seen in previous lectures that using a single tree for prediction is typically not competitive with other predictive methods seen earlier. So the idea here for the current lecture is to introduce methods which will allow combining predictions or output of several trees, and then combining all such trees could then improve the performance on our the decision trees, and then produce prediction methods which are much more accurate and whose performance becomes more competitive or even sometimes better than the other methods we've seen earlier, depending on the context and the problem at hand. Okay, so let's start introducing these methods. The first one we're going to discuss is bagging. So the one issue that was mentioned in the previous lecture is that when we use a single tree, even if we prune the tree still produces predictions with substantially high variance in practice. Okay, so for example, if we take a data set and we split it into two and train the tree on the two different parts instead of the entire data set, well, typically the tree obtained in the two half data sets will be completely different from one another. And this highlights the high variance problem. If we have a linear regression model, we split a data set into two and run it on both the two halves of the model. Typically, the linear regression produced should be roughly hopefully similar between the two parts, whereas for the tree, typically if you use one tree, you have very different outputs. Okay, so this illustrates high variance. Predictions are not very stable when we use a single decision tree. So what we're going to propose here is to use multiple trees and average their output so as to produce more stable predictions with lower variance. So the method we're going to introduce, called bagging, it's a general purpose procedure in the sense that it doesn't apply only to decision trees. You can use bagging for all prediction methods seen, or even those seen earlier, or those we will see in subsequent chapters. Bagging is not limited to decision trees, but it's very useful in the context of decision trees, so we'll present it in that context. So the procedure for bagging involves the three following steps. The first one is to obtain capital B different training sets, where capital B typically it's very large. So this, well, if you see it, when you see that, you say, well, how can I obtain capital B training sets if I have only one data set? I cannot split it into a million or something like that. How do I do that? Well, we'll describe that subsequently, but for now, let's just say it's done. It can be done through bootstrapping. Okay, but we'll explain that later on. Let's assume now that we have capital B different training sets. Then for the second step is for each of these training sets, you build a decision model. So you train your decision tree. For instance, it can be using recursive binary splitting or other methods. And then for the small b tree within where b goes from 1 to capital B, the prediction function obtained from the decision tree is denoted by f hat b. So you have capital B prediction function, one associated to each tree or each training set. And then once you've done that, then you average the prediction for all trees to come up with a total an overall prediction. Okay, so once you have all the predictions for all trees, then the f hat average x, which is the final prediction of the model when the predictors are x, so final prediction of the response for values of predictors x, is simply the average across all the training sets or all of the trees of the predictions made for each individual tree for that value of predictors. Okay, so basically you obtain B training set, you train one tree per set, average the predictions, and then this is how you obtain your bagging prediction. So the question that remains here is how to get these B trees. But before that, before how to explaining how to get capital B different training sets, we'll illustrate the rationale about why this makes sense to try to average multiple predictions. So here, let's examine the variance of the prediction made by the average of all trees. Okay, so the idea here is that predictions from all the different decision trees, they are imperfectly correlated. Okay, so because of that, because of their imperfect correlation, the variance of the average should be smaller than the variance of each individual tree. So let's see that the variance of the average, well, it's 1 over b squared times the variance of the sum of each prediction for each individual tree. And here, this variance, well, the variance is the covariance between x and x. So we can express that variance as the covariance between this sum and this sum. And then take the summations outside of the covariance because the covariance is a linear operator. And here we have covariance between the prediction B1 times the prediction B2. And here, if the predictions are imperfectly correlated for some combinations of B, then this would be strictly smaller than B squared times the variance of one individual tree. So let's see why. Let's have this. So this, the covariance, it's equal to sigma. It's the standard deviation of FB1 hat. Standard deviation. I'm going to drop the x in the notation just for simplicity of notation. So the covariance, as you've seen, it's the product of the two standard deviations times the correlation between FB1 and FB2. Okay, and these two guys, because so if all the training sets we have are distributed in the same way, we're gonna see next that this will be the case through our bootstrapping procedure. But assuming all training sets have been generated in the same way, and the tree is calibrated in the same way in each of such data sets, then these two people should be equal because the estimators from all different training sets will be identically distributed. So this should be equal to the variance between here FBI and here this guy. So the product between this is the variance, and this guy, we assume that for some B1 and B2 this is smaller than 1. So for some combinations we have this being smaller than 1. So because this is the case, this summation here will be strictly smaller than this double summation times the variance of BI. And again, the variance of all F hat BI is completely identical. It's a constant because if all the data sets are generated in the same way and the trees are trained in the same way. So here this double summation has b squared terms, so this becomes this, and here the b squares cancel out and we obtain this. Okay, so this means that if the predictions from the various trees are imperfectly correlated, then the variance of the average should be strictly smaller than the variance of one individual tree. So it makes sense to average predictions across trees so as to reduce your variance of your predictions. And as we've seen earlier, predictions with lower variance, all else equal, have lower mean square error of predictions for new observations, so these are better predictions. Okay, so this is the rationale for using an average of the many trees in the bagging procedures instead of a single decision tree, which is so as to reduce the variance of predictions. Okay, so as we just mentioned, in practice, of course, we don't have capital B training sets, so we can have, typically we have one training set. Sometimes we might be able to subdivide it, but not into a million parts. So let's say we want capital B to be a million. How to do that? Okay, so the idea here is we're going to use bootstrapping. The bootstrapping procedure entails here that for the Bth training set that we want to obtain, we're going to simulate such training set based on the original set using a sample with replacement. Okay, so for the Bth training set, we're going to sample with replacement n times from the original training set, where the the n is the number of observations in the original training set. Okay, so if your original training set has 1,000 observation, then your new training set for b is equal to 1 will be 1,000 observations from the original data set sample with replacement. For b is equal to 2, you sample with replacement 1,000 times again from the original data set, etc. So because we sample n times from the original data set for each b, of course, in some data sets, there will be duplicates. Okay, so sometimes when you sample with replacement, some observations will appear more than once. Well, in fact, this should always happen, except if you're very lucky in a sense and your sampling with replacement only uses exactly all original observations, but this is very unlikely. So in pretty much all the new data sets obtained through bootstrapping, you will obtain duplicates, but this is how the procedure works. Okay, so now through that bootstrapping procedure, this shows how to generate capital B data sets from an original data set, which is from sampling with replacement for each B from the original data set. Now, if you train decision trees from the original data set, will the predictions from each tree be independent? So you might think that, well, because every sub-data set B was generated like independently using the original data set, you should have independent predictions. But this rationale is not entirely true, because the original data set is fixed. Okay, so although for each generation you might use different randomness to generate each data set, well, the original data set is only obtained once. So because of that, all the new trainings, the new capital B new training sets, they all come from the same original data set. So for that reasons, there's some dependence between the various new data sets, and predictions stemming from all these new data sets, they're not independent. But the idea here is not being independent doesn't mean that you're 100% correlated. So of course, the various data sets, new data sets, will differ in some way, and because of that, the predictions obtained will not be identical and thus will be imperfectly correlated. So it still makes sense to use bagging, because that bagging procedure should reduce variance. Okay, so in the context of decision trees, when we apply bagging, we have capital B data sets and we fit a decision tree for each such data set. A typical practice is when we use bagging, we don't prune the trees. Okay, so we said when we use an individual tree, typically we have a very deep tree, and then at the end we start pruning branches which are not very necessary. Well, for bagging, this is not the case. We don't even care about pruning the tree in practice because not pruning the tree will lead to higher variance, and so but will might increase bias. So why is that the case? Um, it's because when you prune the tree, you reduce the number of branches, and this entails that some observations that might be more dissimilar could be aggregated together in the same subregion, and thus this would lead to bias. Okay, so having less subregions might entail classifying observations further away in the same bucket, which might not be accurate. So because both are different, so this leads to higher bias. Conversely, you have less variance because we see that deeper trees they lead to overfitting. So pruning the tree led to variance reduction. Okay, but the idea here is when we use bagging, we don't, well, not we don't care, but reducing variance is not very important because for each single individual tree, you might have very high variance, but once we'll average decision trees over a million new samples, so let's say capital B is equal to a million, then the variance will be heavily dampened by using all these trees. So because we're able to dampen the variance, we're ready to have a bit more variance in each individual tree, whereas this is acceptable to reduce bias because when averaging trees we don't reduce bias but we reduce variance. Okay, so the idea is we'll have each individual tree with low bias and high variance. Once we aggregate the trees, the average prediction should have both low bias from all low bias of each tree and low variance because we've averaged all these trees. Okay, so this is the idea. When we use a bagging procedure, we don't typically people don't prune trees. They just uh, train very deep trees with many nodes for each data set and then average all these trees. So in practice, people have investigated these methods, of course, and it has been shown that for many problems, bagging was able to produce very impressive improvements in accuracy by combining either hundreds or thousands of trees into a single procedure instead of having an individual decision tree. Okay, so in practice, using bagging instead of an individual tree can produce much better results. Some people have applied these tests on true data and they came up with this conclusion. Okay, so we've seen bagging can tremendously improve accuracy in prediction in comparison to a single tree. But however, on the downside, when we average 1,000 trees, the interpretability of the model suffers because interpreting a single tree is straightforward, but interpreting the combination of 1,000 trees, of course, you cannot do that. Okay, so you have more accuracy typically with bagging, but on the downside, you have less interpretability. So depending on what's your what's your goal? Is it to get the most accurate prediction, or is it to have more insight about which variable impact the prediction and how? So you might favor different methods, either individual trees or let's say bagging where you have many trees. Okay, so we said that for bagging, when we use bagging, it makes the interpretation a bit less straightforward. So in that case, there were methods developed to assess the importance of the various predictors in a bag model. Okay, so if you have a bag model, so a model which uses bagging, sometimes in practice you nevertheless want interpretation, and you want to know, well, when I use this bagging procedure with trees, which predictors are important. Okay, so for example, if we use linear regression, this is this question can be an answer to the question of which predictors are important can be provided by, for instance, looking at t statistics of variables or trying to drop them and observe like the performance. But in a decision tree framework, it's also useful and necessary to have metrics which allow providing an answer to this question of what is the importance of the various predictors in our predictions. Okay, so here we will study some one of such metrics next, which bases itself on the average decrease in the sum of square errors, or the Gini index if we're in the classification setting instead of regression, caused by the splits over each variables. Okay, so if every time I split with uh, so, sorry, if every time I split with respect to predictor 1, I have a huge decrease in the sum of square errors, and conversely, whenever I split with respect to predictor 2, the improvement in performance is only minor, then you might want to have this information and know that predictor 1 is more important because it leads to, it's more helpful to reduce or to improve your prediction accuracy. So we need to derive metrics based on this to get that information. So what we will define here is the quantity known as variable importance. So we'll define first the variable importance metric for a single tree, and at the end we'll discuss how to aggregate this metric across multiple trees so as to get a variable importance metric for example in a bag model where you have multiple trees. Okay, so without loss of generality, let's consider a single regression tree. So sometimes I call them decision trees, but if it's applied in a regression setting, often it's called a regression tree. Okay, so consider a single regression tree attempting to minimizing the sum of square errors of prediction in a training set. Okay, so we'll use the sum of square errors, but if we work in a classification setting, all the same ideas can be applied using either the Gini index or the entropy instead of the sum of square errors. So when training our decision tree, we typically take subregions R or regions R and split it into two subregions R1 and R2 so as to provide the best reduction in the sum of square errors. Okay, so this is the recursive binary splitting approach we've introduced earlier, which does that. Of course, there might be other procedures, but this is the standard one we have introduced here. So let's continue working with that. So we can define what we call the squared improvement of that split. So every time we make a split, we can define an associated square improvement, which is defined as the difference of the sum of square errors of all of predictions for all observations into that region R before versus after the split. Okay, so before the improvement square is defined as the sum of squared prediction errors for all observations in R before there was a split minus the new sum of square errors after the split, which means so here this becomes the sum of squared prediction errors for the subregion R1 plus the sum of squared prediction errors for the subregion R2. Okay, so I square is always greater or equal to 0 because whenever we make a split, we can never decrease performance. We always increase performance. Otherwise, the tree simply stops making splits. Okay, so this is the squared improvement. So notice it's I squared, it's not I. Okay, I is the improvement, but this is the definition of I squared. So if you wanted I, you would need to take a square root of this. Okay, so now for a single decision tree T, the squared variable importance of a predictor L is defined as follows. Okay, so the squared variable importance for decision tree L, let's start that again. The squared variable importance for decision tree T and um, predictor L, so L can be anything from 1 to P for each predictor. So for predictor L, the squared variable importance is the sum across all splits that were made. Okay, so if the final tree has j leaves, it means that there were j minus 1 splits made, and for each such splits, there was a squared improvement calculated. So IT squared is the squared prediction improvement at the teeth split. And here, for the variable L, what we're going to do is we're going to sum across all splits where the variable on which the split was made was L. We're going to sum all associated square improvements. Okay, so basically, I squared L is simply the sum of square improvements where we sum across all splits made on that variable L. Okay, so variable importance of predictor 1, we sum the square improvements whenever splits on variable 1 were made. Squared variable importance for variable L is equal to 2. We sum all squared improvements whenever the variable 2 was used for, or predictor 2 was used for the split, and etc. So here this gives I squared L, the square variable importance for each of the predictors. Okay, so we can see that if a predictor L was very useful to reduce the sum of square errors, it should have very high square variable importance. So it should be deemed very important because the square improvements should be high. Conversely, if some variable was not very useful to reduce the sum of square errors, either because it was not used often within splits or because each of the splits only yielded a very low reduction in sum of square errors, then this variable importance should be low. So here, in a bagging model where we have capital B trees, so let's denote all the trees T1 until TB, what we need to do is we need some way to average the variable importance across all trees. Well, how to do that? It's going to be very simple. We're simply, so the squared variable importance across all trees will be simply defined as the sample average across all individual trees of the square improvement for that individual tree. And of course, we do that separately for each variable L. Okay, so for a fixed variable L or predictor L, its associated square variable importance is the sample variance of each of squared variable importance for each individual tree. And finally, once we want the variable importance, we simply take the square root of the variable importance squared. Okay, so we define the square, not the variable importance itself. So the importance is defined from the squared variable importance. Okay, so as we mentioned, this really indicates how helpful each variable was to reduce the sum of square errors. So the one key thing to notice here is if variable importance is high, it means that either well, it can be both, but either like a variable was used very often in splits. So we see that if a variable is used often in splits, then let's go back here, there are gonna be many terms associated with this variable. So this will increase its variable importance. Or conversely, another way to increase the variable importance for that predictor is if you might not have many splits over that variable, but if the splits are very helpful to reduce the sum of squared prediction errors, these terms will be very large, and therefore you'll also have a high variable importance. Okay, so because of that, the higher the variable importance is for some predictor L, the more useful the predictor L is to make accurate predictions. Okay, so this can provide you with variable insight if you want to do statistical inference or to uh, obtain insight from your data. And we can see that using a decision tree method with bagging, for instance, you can define the variable importance and try to understand what's the impact of total impact of each variable, or the importance at least of each important variable, to make your predictions. Okay, so now we've introduced bagging as an interesting way to combine the various decision trees to come up with better predictions. The second method we're gonna introduce is called random forests. Okay, so random forests is another technique to combine various decision regression trees to come up with predictions. So now, in the position to bagging, which was a general approach that could be used with many prediction methods, random forests is applies specifically to decision trees. Okay, so it doesn't make sense to say I apply random forest on a linear regression tree. No, random forests only apply to on a linear regression. No, random forests they only apply on decision trees, not on linear models or other models we've seen earlier. And this is why we use the word forest here. It's really because it applies to decision trees. Okay, so as you can probably expect, random forests, well, when you have a forest, you have multiple trees. Okay, so this justifies the name forests here. So the textbook states that random forests often improves performance over bagging. So I haven't tested that myself, but some people have tested these procedures on many data sets, and in some problems it was seen that random forests could yield improvement over bagging. And let's try to understand why this is the case. So let's consider one fictitious example where you have a data set, you have a response and predictors, and let's say you have some predictor with a very, very, very strong predictive power. Okay, so one of the predictors is very, very, very useful to predict the response. And the other predictors are still useful, but they have a more moderate predictive power. Okay, so you have a very useful predictor and some other predictors that are, yes, useful, but to a lesser extent. So if you use bagging, so what happens in our bootstrapping procedure, we obtain capital B new data sets from the original one, but the capital B data sets, they should have somewhat similar overall distributions than the original data set. Okay, of course their distribution will change, but all the data sets should not be completely dissimilar, okay, because they sample from the same original data set. So in that case, if one predictor is very, very strong, then most likely in all the new various capital B data sets and bagging, most likely in all these data sets, the decision tree might use this very strong predictor in the first stage to split over that variable. Okay, so in that sense, the trees from all the capital new data sets will exhibit some similarities. And is that a good news? Well, for variance reduction, maybe not, because we saw that what we wanted through bagging is to have predictions which are decorrelated in the sense that the lower the correlation between the predictions, the lower the variance would be when we aggregate all these predictions. But if all the trees are similar or exhibit very strong similarities, then they will be more correlated, and the variance of the average across all the new data sets might not be reduced a lot. So because of that, what we would like to do in the random forest is to try to come up with a method where we would have many trees that are average, but we would like these trees not to be too similar together. We'd like the trees to be exhibit some um, di- meaningful differences, and the reason is we want the predictions from the various trees to be decorrelated. We don't want a correlation that is too strong between predictions of all trees, so as to obtain a variance when we average all the trees that is as reduced as much as possible. Okay, so basically we like to try to decorrelate the prediction from all trees by trying to force the various trees to be somewhat dissimilar. Okay, so now for random forests, instead of generating capital B data sets with a bootstrapping procedure, typically you can use random forest by considering one single training set. Okay, so you don't need to derive capital B new training sets. You just can stick with your original training set, but train many decision trees on this original training set based on the procedure we will highlight next. So whenever you generate one tree from a random forest, of course at the end we want to simulate many trees, but for one single tree the following procedure entails using the following. So every time we make a split in the recursive binary splitting approach, what we're going to do is we'll only allow splits to be performed over a subset of predictors where this subset is chosen randomly. Okay, so let's say you have p predictors in your model. So every time we make a split, we're going to randomly pick m predictors from the total set of predictors, and only splits would only be allowed from these randomly chosen m predictors. So the textbook suggests using approximately m being square root of p. So this is a thumb rule. I'm not aware of any theoretical development justifying this, but people have tried this in practice and probably it gave good results. Okay, so the suggestion from the textbook is to use approximately m is equal to square root of p. So the idea, let's say you have p original predictors, m it's roughly 3, it's a bit more than 3, but let's use m is equal to 3. Then what will happen is when you make the first split, you select randomly 3 predictors and you find the best split over all 3 predictors that you can make. All the other predictors for this first split are banned. Okay, so you prevent the tree from splitting over all other predictors than the one randomly chosen. So you make the first split, then at the second stage or second split, you still randomly pick again 3 predictors out of the 10, and you only allow splits over these 3 predictors, etc. Okay, so the idea here in the random forest is whenever you make a split, you randomly select predictors on which splits would be possible, and all other predictors are banned in the sense that you cannot split over these for that particular split. So using this forces some form of dissimilarity in the prediction or in the various trees. So for example, if we go back to our original example where we have some very strong predictor, well, in this case, for some of the trees generated by the random forest procedure, this very strong procedure might be banned in the first split, for instance. So if it is banned, it forces the tree to use other predictors to make the first split. And because of that, this forces dissimilarity within the tree. So not all the trees can be exactly identical because various predictors are banned in various steps in the various trees. So you obtain multiple trees generated from the same original data set, but which exhibit some form of dissimilarity. So because of that, because the trees are all dissimilar, they're imperfectly correlated, with the correlation hopefully not too large because of these dissimilarities. So because of that, when averaging all the trees in a random forest at the end to make your total prediction, you should be able to substantially reduce the variance. And hopefully this comes at the expense of limited additional bias. Okay, so you might create some bias by banning some predictors at some points, but uh, if the increase in bias is not too large, then the reduction in variance might be worth it, so as to produce more accurate predictions in the mean square error, in the sense of mean square error for new out of sample predictions. Okay, so now we've introduced bagging, random forests, and we'll study a third approach called boosting. Okay, so once again, boosting can be applied not only for decision trees, it can be applied in general for various prediction methods, but we will illustrate it in the context of decision trees because it's very useful in that context, and because the textbook does that, so I'll just follow the approach of the textbook. Okay, but boosting, it's a general methods which can be applied not only to trees but also to other methods, but we'll study it now in the context of decision trees. Okay, so once again, the idea of boosting is to combine predictions made by various trees to come up with a better prediction in comparison to using a single tree. And once more, we will illustrate boosting in a regression context, but we will. I just wanted to let you know that there are methods of boosting that can be applied in a classification setting, but we won't study these here. The details are out of scope, so we'll focus exclusively on the regression case for boosting here. Okay, so for bagging, what we did earlier was to take the original data set and come up with capital B new training data sets by sampling with replacement from the original data set. Okay, so all these new data sets could be generated in parallel. So one did not depend on each other. And this is very good, for example, if you want to use parallel computing. Bagging is very convenient because the predictors, the trees trained over all such new data sets can be computed in parallel, and they don't depend directly on each other. Conversely, for boosting, we cannot do that because the trees from once again, we want to calibrate or to train a collection of trees, but the trees, they are not constructed independently from each other. Instead, they will be constructed in sequence. So the second tree will depend on the first tree, the third tree will depend on the first and second tree, etc. So there's some form of dependence between the trees, so we cannot do that in parallel. The trees are built sequentially. And the idea here is that is applied by boosting is incremental learning. Okay, so for example, when you learn, let's say English or even mathematics, you don't try to learn everything at once. Okay, so basically you learn easier or more obvious concept, and once you have this, then you start refining your knowledge by getting a bit deeper and then deeper. So you progressively refine your knowledge so as to become more knowledgeable and be more accurate when you consider notions. And here boosting uses a bit the same idea of incremental learning. So you learn the most obvious patterns at first, and then you look at your errors you make, and every time you make errors, you train new model on your errors to learn from your errors, and sequentially refine your predictions until you're satisfied with your predictions. Okay. So what happens in the decision tree is the following. So you start with predictions that are let's say 0 or really bad predictions, then you train a decision tree uh, on the original data. And then once you come up with these predictions on your original data, you get prediction errors known as residuals. And then what's going to happen on the second step, you're still going to train a decision tree, but your new responses will not be the original variables, but rather the residuals or the errors you make. And you try to fit a decision tree to errors so as to try to understand if there are remaining patterns in errors. And if so, then you should capture them and continue. And then you get a second set of errors from the second decision tree, which hopefully should be smaller. And then from here, this is the outstanding errors you make, and then from this you train another decision tree, come up with residuals, and then on these new set of residuals, train another tree, produce errors, get another set of residuals, etc. Okay, so you basically fit all the decision trees in sequence, and at a given iteration, the trees is fit not on the original responses, but you use the errors or the residuals made from the previous tree to train your model so as to learn incrementally. Okay, so if you do that in the context of decision trees, so of course we said trees, but every time it could be another prediction model. Okay, we said boosting applies generally. So what you can do is every time you train a model on residuals, it's not forced to be a tree. It can be some other model, but here we're going to consider trees just for the sake of explanations. So at each step, contrarily to bagging, the trees we will make are typically very small. Okay, so we said that for bagging we train very deep trees so as to reduce bias. Well, for boosting, it's gonna be the opposite. Okay, so typically on every time you make an improvement, you want to learn incrementally a bit at the time. So you make on each individual tree, there will be very few splits made. Okay, so the rationale behind that is methods which learn too fast tend to overfit. Okay, so if you want to right away produce extremely accurate predictions for your training data set, then you will overfit. So of course there will be no outstanding error and it looks like you've done very well, but no, it's really because you've overfit your data. So for that reason, to avoid overfitting, we'll want the algorithm to learn very slowly in the sense that on each decision tree we make, there will be very few splits. So the boosting algorithm we will introduce a bit more precisely next depends on 3 parameters. So capital B is the total number of trees that are built. Lambda will control what we call the learning speed. And D will be the depth or number of leaves for each regression tree in the procedure. Okay, so here lambda will be the learning speed, but as we just discussed earlier, learning speed is also somewhat related to D, because if D is very deep, then you're assumed to try to learn many more details more quickly. Okay, but nevertheless, D will refer to this as the depth, and lambda that we will introduce later on in the next slides is defined as the learning speed. Okay, so in practice, how do we choose all these parameters? So capital B is going to be in practice chosen through cross-validation. Okay, so here we need a discussion about this. If you use bagging, the larger B is, the better it is. Okay, so you cannot have a B that is too large in bagging. Okay, so for the larger B is, the larger your variance is reduced for predictions, and this does not create issues. Conversely, for boosting, the right value of B cannot be too large because larger B can produce overfitting. Conversely, smaller B's produces insufficient learning, so underfitting. So there's a suitable value of B, which would provide the optimal trade-off between underfitting and overfitting, and typically capital B is chosen through either cross-validation, or it can be out-of-sample prediction assessment. Lambda, the learning speed, often it's chosen in an ad hoc manner. Okay, so again, learning speed, this could be, you could try to optimize this looking at cross-validation, for example, but in practice, people often set up this value like heuristically. Let's say lambda is 1% or 0.1% or something like that. And finally, D, the depth of each tree. Also, it's chosen manually often, but its value is very small. Okay, so it can be 1, 2, or 3 or something like that. Often the value 1 is used, and when the value 1 is used, the trees, we refer them as stumps. Okay, so stumps is trees with single split when used in a boosting context. Okay, so we now provide the boosting algorithm a bit more precisely. So here in the next slide, we're gonna define the following quantities. Okay, so P hat Bx stands for the prediction of the response after made by the Beath split. Okay, so the not the Beath split, sorry, the Beath decision tree. Okay, so we said that at the Beath iteration, we fit a decision tree on existing residuals as response and using the original predictors. And the prediction made by the Beath tree is denoted by p hat, so prediction made by the Beath tree when the predictor value is x. Conversely, epsilon hat IB is the prediction residuals made by the Beath tree. So the Beath tree makes prediction errors. So recall that these predictions error is by comparing their predictions not to the original value, but the residuals from the first step. And when comparing residuals from the first step through the current prediction of the Beath tree, then you obtain new residuals, which are denoted according to this. Okay, so epsilon I refers to the residual for the ith observation made by the Beath decision tree. Okay. Okay. Okay, so maybe, sorry. I just want, seeing this, I want to clarify something here. P hat B is not the prediction made by the Beath tree, but it's the cumulative prediction made after all first B trees were made. Okay, so sorry for that. The prediction made by the Beath tree will be denoted F hat B. So this is the prediction made by a single tree B. But here, P hat B, it's not the prediction made by the Beath tree. It will be the cumulative prediction made after the first B trees were trained. And here, these epsilons are prediction residuals made after B steps. So it basically made from okay, so sorry again. These are residuals, which are prediction errors obtained after B small B trees were trained. Okay, so sorry, I referred first to them as predictions and errors made by the Beath tree, but I'll correct myself. I'll say instead that these are predictions and residuals not made by the Beath tree, but by all first B trees. So after the first B trees were constructed. Okay, so sorry for this ambiguous explanation. Okay. So the boosting algorithm works as follows. So originally at the onset, we make a prediction of 0 for all values of the predictors. Okay, so it's a very bad original prediction. And the residuals at the first step, they're simply equal to the original responses. Okay, so if your prediction is 0, then your prediction error is the responses themselves for each observation in the training set. And then for all iterations, so for all trees that we construct, we repeat the following procedure as follows. So you fit a decision tree, f hat b, on the following data set. So your predictors are the original predictors, but your response you're using is not the response variables unless you're in the first iteration, but these are rather the current residuals made after your first B trees were obtained. And then once you fit a new decision tree, FB, you will update your predictions and residuals as follows. Okay, so the new predictions after B trees will be the predictions from the first B trees plus your prediction made by the new tree, but you will weight them by some constant lambda. So we see that lambda here represents the learning speed, and we don't fully update the predictions by fully incorporating the new fit, but we rather only incorporate a fraction of it. So the idea here is incremental learning. You want to gradually correct the errors you make instead of fully correcting them. And the idea is we want to remove instance of overfit. Okay, so if lambda was equal to 1, probably you'd learn too much and overfit your data pretty quickly. So for that reason, the improvements or the corrections made in prediction is only a fraction of predictions provided by the new tree. And for that reason, clearly, if you have added this quantity to your predictions, then your residuals should be offset by this quantity. Okay, so if you improve your, if you modify your predictions by this term, then of course your residuals would be reduced by this term. Okay, so so here there should be an I, but your residual for observation I after the B tree was trained is your previous residual minus the correction you made in prediction. So this is lambda times f hat b xi. Okay, so we see that this method entails gradual modifications of your prediction by building new trees on each step, and for each of the trees, you train it not on the original responses, but rather on errors made at the first step, so as to try to correct mistakes that you're making instead to trying to learn from scratch on every step. And finally, once you've trained all your capital B trees, then you can use the following recursion to see what your total prediction looks like. So your prediction after the B trees were trained, as per the previous rule, it's the prediction after your B-1 B tree was trained plus lambda times your prediction of your B tree. And here, this guy, you can increment it by you can still use that rule. So if you replace capital B by capital B minus 1, you can express this as capital B, P capital B minus 2 plus lambda F B minus 1 plus lambda FB, and etc. So if you repeat this procedure capital B minus 1 times, then ultimately at the end you get the following, which is that your prediction made for when the value of your predictors is x. So for an observation whose predictors is x, your prediction you make, if you apply this, is simply summing across all your trees that you've trained lambda times the prediction made by the B tree. Okay, so here we see that instead of averaging the trees for the boosting method, we're going to sum prediction made by all trees and weight this by the learning speed lambda we've considered. Okay, so this is how the boosting procedure works. And again, as we said earlier, f hat here, we use decision trees here, but it can be other methods that we could consider instead. So it can be other, let's say, linear models or GLMs or anything that we would want to consider. So this completes the chapter. So thanks for listening, and I'll see you next time.